But if I were to flip 3 coins, and let's say they landed as you see them over there on the right side, how could you describe the result of what you got for your 3 coins? This looks like heads, tails. Okay. So one example of something we could write as part of our sample space would be that outcome. The first coin is a heads, the second coin is a heads, the third coin is a tail. Just shout out, what are some other results you could get when flipping 3 coins?
Heads, heads, heads.
Heads, heads, heads. Very good. What else?
Tails, tails, heads.
Tails, tails, heads.
Tails, tails, tails.
Tails, tails, tails.
Heads, tails, heads.
Heads, tails, heads.
Tails, heads, tails.
Then tails, heads, tails. Do we have them all?
Tails, 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 tails.
Okay, bless you. I heard a tails, heads, heads. I try to agree, I don't think we have that. And
Head, tail, tail.
head, tail, tail. Okay. Now, some of you might be looking at that list and you're saying, well, you're writing some of those more than once. Okay, what would be some that you might think are very similar to each other? Okay, heads, tails, tails, tail, tail, heads. Right? You're looking at that and you're saying, well, heads, tails, tails, and tail, tail, heads, it's still the same number, like 1 heads, 2 tails, right? And there's another one up there. Which one? Tails, heads, tails, right? Okay. That could be something that we use, like, let's say I'm going to ask you in terms of probability. What's the probability you flip 3 coins and get 2 tails and 1 heads? Well, there's 3 ways to do it out of 8 total outcomes. So you'd have a 3 out of 8 probability of doing that. But we count in sample space, we count those as different events because each coin is landing on a different outcome, heads or tails, and that changes. And so we really should have better probability, 3 out of 8, of getting 2 tails and 1 heads than we would of getting all tails, right? If I said, what's the probability of getting all tails, you would just say 1 out of 8. And don't you think that should be harder to do, to get 1 of all the kinds than to get 2 and 1? So we do want to list those in the sample space. Okay, so I saw some people who were kind of looking at that funny, and that's okay. I totally get that, but we're going to count them differently. Now, I'm going to have you write somewhere in that little area that you have 8 total outcomes, and I want to talk about a little sort of cheat for counting your total outcomes. This can be really helpful later on if we're working with bigger numbers and we don't want to list out that sample space. It's called the fundamental counting principle, and what it does is it says figure out the number of ways that each individual event can occur and then multiply them together. Okay, so I'm going to go back over here to my coins and I'm going to call this coin number 1. How many outcomes are possible for coin number 1 if you just flip that 1 coin? 2, heads or tails. How many outcomes are possible for coin number 2? 2, heads or tails. And how many outcomes are possible for coin number 3? 2, heads or tails. So the fundamental counting principle says you just counted up the outcomes for the individual events, multiply them together, and that's your total number of outcomes. Is that what we have? Yeah, they correspond to each other. So you can use that as a cheat if you don't need to really list out your whole sample space and you just really need to know what your total number of outcomes is. Any questions on that? Okay, so we're going to move right along to the next set of examples. And part A, I think you'll probably be very good at, if you just roll one six-sided die, what are your possible outcomes? 1 through 6. So we would just list them. 1, 2, 3, 4, 5, 6. We're done. So we can all agree to that. The second one, part B, I want to do this one time with you so we can talk about a couple of things when rolling 2 dice. And then you'll have all the outcomes listed in your notes if you ever need to look at them again. They're all here. So we'll do the sample space one time for this. What happens if you roll 2 six-sided die? Okay. So let's think about it like, okay, I'm going to roll the first dice. Or first die, and let's say it rolls and I get a 1. Okay, first die is a 1. What are my possibilities for my second die? 1 through 6. So we need to write all those pairs because they're all possible. So you do 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. But then we would ask ourselves a different question. What if, instead of rolling a 1 on the first die, I roll a 2? Then what would my options look like? 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Okay, now something to pay attention to. How many ways can you roll 2 dice and roll a 1 and a 2? There's 2 ways to do that. You could get a 1 and a 2 or a 2 and a 1. And we have to argue that those are actually different. Here the first die is a 1, the second die is a 2. Here the first die is a 2, the second die is a 1, and those are different. If you're having trouble with that, I tell you to imagine like colored dice. So like let's say we have a red die and a white die. If the red die is 1 and the white die is 2, that's an outcome. But what if the red die rolls a 2 and the white die rolls a 1? That's a different outcome. That would still have the same numbers, but it counts twice. Just like tails, tails, heads, and heads, tails, tails. We count them twice. Could you complete the list for your sample space? You'd have to make a row or a column for every number on the first die. Go ahead and do that so you have all the outcomes somewhere in your notes. How many outcomes should you have at the end? 36. And think about that in terms of the fundamental counting principle, just like we did for the dice. How many outcomes are possible on the first die? 6. How many outcomes are possible for the second die? 6. So 6 times 6 is 36. There should be 36 total outcomes. The other thing that I'd like you to kind of look at in your list is we talked about 1 and 2 versus 2 and 1 being different. And notice that's the same for every pair of numbers, like 2 and 4 and 4 and 2. There's always 2 ways to do that pair, okay? Except for the doubles, okay? How many ways can you roll a 1 and a 1? One way. The first die is 1, the second die is 1. There's one way to do that. How many ways can you roll a 2 and a 2? One way. And if you look at that diagonal that is all of your doubles, there's always only one way to do that. Okay, and then there's 2 for every other. Okay, so that's a brief overview of sample space. Let's move on and talk about probability. Let's get to the good stuff. Probability. Go ahead and jot down the definition. Probability is the likelihood that an event will occur, or the chance that an event will occur. Probability comes with its own notation. It looks a lot like what we studied earlier in first semester called function notation, which we would always write stuff as like f of x. Now when we talk about probability, we can write it as like p of a, where capital P in function notation represents probability. So when you read that in other textbooks, you're always thinking, oh, okay, they're asking about the probability of an event. If I put an A inside the parentheses, then I'm referring to like some event A. You can name your events with like capital letters. So maybe we also have event B. So we could do a P of B. Or you're going to see me do this on our example slides later. You can put whatever you want in that group of parentheses so that it represents what probability you're finding. So if we're talking today about the probability of having a snow day tomorrow, we could write out our probability notation like probability of snow day. So you can put whatever you want. How many people have done their snow day calculator? Nobody? Oh, Sierra, what did your snow day calculator say?
So it's like 95%.
95?
Yeah, well, that's not what I use. Sometimes it's wrong.
It's wrong. You mean this snow day calculator is not legit?
Well, hopefully, but...
That's a lower estimate. It must be going down. My student's second hour said 99%. I didn't even know there was such a calculator in existence. Okay. Anyways, moving along. Talking about probability. Probability happens on a scale. And the big thing that I want you to know is that your scale is bounded on both sides. Your scale for probability is bounded by 0. There's nothing lower than a 0 probability. So when you look at the scale at 0, the event will absolutely not occur. It can't get any worse than that for probability. On the other side, probability is also bounded by the value of 1, which is kind of like 100%. And that means it absolutely will occur. There's not a question of doubt, okay? So it doesn't get any better. You can't have somebody say like there's 110% probability of something. It doesn't get better than 100, or it doesn't get better than 1. Okay. And then somewhere in between are all the other probabilities. The closer you are to 0, the less likely it is to happen. Think about winning a Powerball, 1 out of 292 million or billion. Million? I can't remember. It's not very good. And then things that are likely to occur, our snow day calculator has a set 0.95, so things are looking pretty good for tomorrow. And then in the middle there's a 0.5, which would represent something that's fair, meaning it's equally likely to happen as it is to not happen. Raise your hand if you can give me an example of something that's 50-50 in the real world. Flipping a coin is a great example. As long as the coin is fair, right? So that you haven't chosen a weighted coin. Sahel, I'm not accusing you of anything. I never think you're doing such a thing. I don't know why that happened. My smartboard has been acting funny all day. Give me a second. Next up on your closed notes is something called a compliment. This is spelled differently than the kind of compliment we give each other when we say, hey, you look really nice today, or wow, you really rocked it on that test. That was awesome. Okay, that would be spelled with an I in the middle instead of an E. So this compliment is more like when you think about complementary angles in geometry. And here we talk about like complements are the probability that something does not occur. So we're talking about the probability of a snow day. The complement of that would be the probability of no snow day. Okay. Now, it has its own notation as well. Its notation looks very similar to what we saw last chapter with our reference angles. It's got the little prime or the apostrophe. So I would read that as A prime, but in terms of a probability context, I might say that's the complement of A or that's not A. And I think you guys, in terms of logical sense making, you're very good at figuring this. So if Sierra's snow day calculator says the probability of a snow day tomorrow is 0.95, what's the probability that there is no snow day tomorrow? 5%, 0.05. How did you calculate that? What does it have to do?
You just subtract.
Yeah, subtract from 100 or subtract from 1. It has to add up to 100%. The probability of something occurring and something not occurring has to be a total of 1. Okay. So to calculate complements, we would take the probability of an event not occurring, set it equal to 1 minus the probability that it does occur. So sometimes complements are helpful when you're calculating probability because, like, let's say, for example, we're tossing 3 coins. What's the probability I toss 3 coins and I get at least 1 tail? Well, that's like the opposite of getting no tails, right? So if I could just figure what's the probability of getting no tails, that would have to be heads, heads, heads. Then I could just subtract that from the probability of 1. So 1 minus 1/8, I'd have a 7/8 probability. So it makes life a little bit easier. Oh, there it is. Calculating probability. This goes underneath complement. There's like a little P of A equals. You're going to type the formula for calculating or write the formula for calculating probability. I usually just sort of abbreviate my formula and I say the probability of event A occurring is equal to favorable over total. Favorable meaning it's the number of ways A can occur, total being the total outcomes possible. And then off to the side there on your closed notes, you've got space for the types of probability. You can jot down theoretical, experimental, and geometric, and I'll talk about those here in just a second. So if we wanted to give an example of, basic probability, favorable outcomes over total outcomes possible, I could give the example of, like, let's say I take the 21 of you and I put your names into a hat. I write your name on a piece of paper, throw it into a hat. What's the probability I reach into the hat and I pull Kyle? 1 out of 21. The favorable outcome is Kyle's name. There's 1 Kyle. We would have 1 out of the 21 total. What's the probability I would reach into the hat and pull Riley?
2.
Should be 2 because we've got Riley and Riley who's absent today. But if I put both of their names in, it would be 2 out of 21. Okay, so that's favorable over total. Now, here's another, that would be more of like theoretical probability. That's what should happen in theory based on the number of names that are in the hat. Experimental probability is based on some experiment, survey, history, something that's already happened. So let's say I put all 21 of your names in the hat, and then I start pulling names, and I do it 10 times. Okay, so I run 10 trials. And during those 10 trials, I pull Jacob's name 3 times. That's out of theoretical probability. Jacob has an experimental probability of having his name pulled 3 out of 10, almost 30%. okay, which is way higher than whatever 1 out of 21 is. Okay, so experimental doesn't always match theoretical. It's what did happen as opposed to what should happen. Okay? And then geometric probabilities usually involve like measurements, length, area, or volume. Most of our geometric probabilities are going to be area problems. So, let's see if I can get this to come down. I didn't leave you a special space on your closed notes, but you've got those 3 types of probabilities written off to the side. I think you can just draw an arrow from geometric and maybe jot this one thing down. Most of our problems are going to be shaded region problems, and so it's going to say like, you randomly throw a dart at this target. It's equally likely to hit anywhere inside of the target. What's the probability you land in the shaded region? So all you have to do is calculate the area of your shaded region and divide it by your total area. And that'll get you geometric probability. If it were volume, you'd just be comparing 2 volumes instead of areas. Okay. Now, below this I have 3 formulas which I expect everybody in the room to know. So if I put a question on a quiz or a test with these shapes, you would be able to come up with them and I don't have to give this to you. If you don't know it, then you should write these down. The first one is the area of a rectangle or a square. I assume you know length times width. If not, write it down and study it. You'll need to know it. I also assume you know the area of a triangle is base times height divided by 2, or you might say 1/2 base times height. And the last one is a circle. I assume you know the area of a circle is pi r squared. If you don't, write that down, study it, make sure you know it. So those would be fair game for quizzes and tests. I could put a shape with some shaded area, and you would have to calculate those areas without formulas. Okay, next up we're going to do a quick activity at the bottom of that paper. We're going to try to squeeze it in here real quick, and then maybe do 1 or 2 of the examples on the back side. How the activity will work is, you'll work with your table partner or shoulder buddy, and I will give you 1 die. You will roll the die 10 times, no more, no less. Okay? And you will record your data in line 3, and then you will calculate your probability in line 4. Okay? We're going to complete 1 and 2 together here before we get started, and then we'll complete line 5 and 6 as a whole class at the very end and kind of compare what happens. So let's start with line 1 and 2. That's your theoretical probability. If you are rolling a die, how many ways can you roll a 1? 1. How many ways can you roll a 2? 1. 3, 4, 5, and 6 are also 1. So they each have a favorable outcome of 1 in theoretical probability. How many total outcomes are possible when you roll a die? 6. So total outcomes in line 2 is 6. And we're going to calculate their probabilities, favorable over total. Okay, favorable over total. So we would have 1/6 in each of these rectangles. This is in the non-shaded part of the table. And you might want to have out a calculator. Can somebody with a calculator give me a decimal to the nearest hundredth for 1 divided by 6? Riley, what are you getting on yours? 0.167. I'm going to just, for space reasons on my smart board, I'm going to write 0.17. But that would be true for all of these, correct? So we're going to have you experiment rolling your dice exactly 10 times, no more, no less. So in line 4, you should have the number 10 there. And then you're going to see how your probabilities compare to the theoretical probabilities. So I'll give you the die, you can start rolling. I tally my results in line 3 and then use those totals to get my probabilities in line 4.
Do you want us each to roll that one time?
Nope, one pair rolls 10 times total. Pass one back to the guys behind you. Pass one to the guys behind you. And you guys can roll together. And I'll just have you record your own. I think you can handle it.
Oh, you just tell us.
So roll it, record it, roll it again 10 times. So if you roll the 4, mark it there. In line 3. Okay, so what we did was we calculated first the theoretical probability in line 2. And then in line 4, you did your own probability with experiments of 10 trials. And, you know, probably a lot of people in line 4, we had some high ones, we had some low ones. What are you noticing in line 6 if we have 100 trials instead of 10? It seems to be more accurate compared to the theoretical probability, right? It seems to be matching more closely. What do you think would happen if we rolled the dice 1,000 times? It'd be even closer to 0.17, right? So the more trials that you have in an experiment, the closer you'll actually get to experimental probability, or sorry, theoretical probability, if it's actually fair. If it's not fair, if the dice is rigged, okay, then that would be a whole nother issue. Okay, but if they're actually fair, we'll get closer and closer to that 0.17 mark. So that's what the, you guys have like a think, ink, pair, share on the back at the very top. That's what it's asking if you flip your papers over. It says, what do you notice about the experimental probability if you increase the trials? Your answer should be something like, it gets closer to theoretical probability. But so we can do 1 or 2 examples. I'm going to skip that. Okay. And your first example is the example with the table and the Super Bowl. Okay, here's the thing about some of these basic probabilities. That problem is really long, but once you read through it, it does not take very long to answer. If I kind of skip all the mumbo jumbo about the setup, my question is, what's the probability that a randomly selected respondent found the shampoo commercial to be the most entertaining? So I'm thinking the probability I liked the shampoo commercial. What's the favorable outcomes for the shampoo commercial in the Super Bowl? 76. What's the total outcomes possible? 250. If you read at the very beginning, it says you have a 250 group, or you could add up all those numbers, right? Okay. And then I think this comes out to be like 0.30 maybe. Okay. I would usually just go to my calculator and do decimals to get my answers. So that's one where it's experimental, it's coming from a table or survey, and it's very easy to do. I want to show you the one other example with the 2 dice and getting a sum of 5 or 12. Okay. So I would probably set up my probability like this, the probability of getting a 5 or 12, and then a sum of 5 or 12. Off to the side, I would do my work, like how many ways can you roll 2 dice and get a 5? What does that look like? You could roll 2 dice and get a sum of 5. A 1 and a 4, a 2 and a 3, a 3 and a 2, a 4 and a 1, and that limits all the ways to get a 5. How many ways can you roll a 12? No. Sum of 12. 6 and 6. And then that's my total favorable outcomes, right? So how many ways can you roll those sums? 5 out of, what's the total outcomes when I'm rolling 2 dice? 36. 5 out of 36, it should be a little less than 0.17, because it's a little less than 1/6. Now, we didn't get through the other 2 examples, but you have some experience with probability prior to this class, so I think you should be able to complete. The 10 problems are at the bottom of your closed notes. Okay, so the homework assignment is at the bottom of your closed notes. If I see you tomorrow, please